All right, good afternoon and almost evening. It's a pleasure to be here. My name is Nicholas Kotov, and I represent here the materials science and chemical engineering. I'd like to continue the journeys about the biomedical investigations. And I have to say that my journey started with deep skepticism about AI and machine learning. I did not like it, I did not trust it, I did not understand why it should be better than us. Well, these results will show you that I changed my mind dramatically. So we started with the idea that interactions of proteins and nanoparticles can be very much identical in many ways, because some nanoparticles have the same size, they have the same amino acids on the surface, and they can also have a very complex shape. And from that, we started looking into how we can design the inorganic nanoparticles that would be much more stable than, for instance, the proteins for making the complexes with the target proteins. And in this talk, I'll show you the results about these two portions that are related to how we design such systems and how we use the machine learning for them, and how we can actually succeed in these very complex structural interactions. If you remember your textbooks from biology and maybe from chemistry, Emil Fischer was the first scientist who proposed that the proteins and the molecules that they interact with form a very sophisticated, tight complexes like lock and key. The idea is fantastic. The few, let's say, 100-something years after that, we're still learning all the intricacies of that. And for example, we can now predict fairly well using AlphaFold and other tools if the molecule is small and the protein is not very changeable. So as soon as the protein can have multiple conformation, that becomes a problem. And on top of that, this is not what I was set up to do. We learn it, there is a concept, but the idea that I want to look at is how the inorganic nanoparticles that are not amino acids, that are not actually very biological, can do the same job. And the variety of shapes are amazing. The variety of interactions are amazing. And that required us to find the language that can speak to nanoparticles and speak to the proteins. Finding that mathematical toolbox that can connect the organization of inorganic materials and biological materials is the key, and the machine learning can definitely help in establishing it. So we started with the idea that proteins have distance matrices that you can see on your right, and they describe how far amino acid here is from the amino acid from the other protein. And this is a matrix, X and Y's. And from that, we started developing this language. We dropped the idea that we have to use amino acid sequence as an AlphaFold, for example, and instead we use true geometry. So if it's a lock and key, it has to be based on the geometrical relationship. So if it's helix left, it has to be compatible with helix left, not the right one. And we developed and utilized structural descriptors that have been in the field and integrated them with the new ones. So the chemical descriptors are fairly common. These are charge, hydrophobicity, number of carbon atoms. There are geometrical descriptors that, for instance, describe how concave this structure is, or how chiral this is, or how enveloping this pocket is. And on top of that, we added the descriptors which are called graph theoretical descriptors. So imagine a protein that can have a reconfigurability in its structure, which, as you remember, is a trouble. And now we describe all the points where it can reconfigure and where some rotational or flexural motion can happen in that molecule with nodes and edges. And it turns out that as soon as we apply graph theory, we have an avalanche of potential structural descriptors which are specific to the graph theory. On top of that, these structural descriptors are equally applicable to organic species and inorganic species. This is the language that we were looking to find. Among those structural descriptors which shows specifically chirality, because so far both AlphaFold and many others, PPI, the protein-protein interaction models, actually fail. And AlphaFold cannot actually distinguish left and right. And we introduced specific descriptor for that called Osipov pickup-Hornberg chirality index. And as you can see, on the surface of one protein, there are many areas that can be positive and negative. So we packed it all in the matrix. We started looking at how one protein interacts with another protein and reconfigures. And in that way, we started using, say, some of the parameters called Equarius, which describe exactly that. If the node or radius is highly negative, it's reconfigurable. From that, we started choosing which parameters could be excessive or correct. As you learned here today, or you learned from your own experience, if you have too many parameters for the machine learning, it's actually bad. Because then the model becomes skewed, it's slow, and it actually gives you unpredictable results, because the parameters need in the mathematical terms orthogonal or independent. And we excluded a lot of chemical parameters previously used from the consideration, because the correlations between are way too large. And from that, in fact, the graph theory, it turns out to be one of the most reliable and orthogonal metrics that we have. I'll skip a few things. This would have been a table that would indicate to you that we used a number of machine learning protocols, support the vector machine, a random forest, and XGBoost. They showed the most accurate prediction. And if you could trust me, the data in this table should have shown you, even if you don't use the traditional chemical parameters, these parameters that have been very strongly correlated, you can actually get more accurate results. And now I started changing my mind from being very skeptical about machine learning to something, wow, I can learn something new. Just to give you an example, these are the predictions of actual interacting sites of protein and protein with comparison of what the ground truth is from the proteins that have not been incorporated in the database for training. There are multiple proteins that we tested, and every time it's 95% accurate. Now you expect that we try to include, and this is transfer learning, so we transferred the learning from proteins into the nanoparticles, stating not explicitly, but in our chemical terms, that they're actually identical. And it turns out that they actually are. And for instance, we got accurate predictions for the carbon nanoparticles or carbon tubes, or if you like, virality. We learned that if you take oppositely chiral nanotubes, you get oppositely chiral interacting sites on them, which was reassuring. So how does it help people? Well, quite in practical terms, we recently transferred that not only in from the general consideration it works, but actually to the predictions of the nanoparticles that can do some biomedical interactions. And this was done, I have to highlight, in collaboration with Professor Chuanlai Xu from Jiangnan University in China, and Professor André de Moura from Sao Carlos in Brazil. I have lots of collaborators, but these are my very favorite ones for many reasons. We made a number of nanoparticles and started asking questions. It was actually during the COVID. How do we transfer the particles that would be better than antibodies for treatment of COVID virus? As you remember, there were a lot of problems with treatments. And it turns out that the particles with that shape, that are chiral, that have a lot of complex interactions with the protein, have been predicted by the machine learning protocols that they have a complex with RBD peptide on the spike of the virus. These are the parts which actually interact with your lung cells and other cells. And if it is blocked, then the virus cannot attach. Well, we started testing it, and initially we tested just a simple, just a segment of S protein, and we saw very efficient agglutination, which is good. And after that, we started asking questions. So if the lock and key interaction works, then slight change of handedness must change the interactions and the strength, and it did work. In fact, if you look at the numbers for affinity for the constant of binding of nanoparticles to S protein in the virus, it's actually 10 times higher than for antibodies. This is really encouraging. Now, we started comparing so that we could learn more, and Andre had done the machine learning, the molecular dynamics protocols, and we compared the very, very lengthy, requiring multiple supercomputers to be engaged predictions that you can see here with the predictions of our model that can work on this laptop. It's absolutely identical. And after that, we were very encouraged. We started testing it at mice, and it worked there as well. And it turns out our nanoparticle not only working in theory, but they're working in vivo. And for example, if we have using these nanoparticles as a prophylactic or as a treatment, we have a substantial reduction of the infection and disability in mice. One thing that I would like to highlight, we need to distribute the vaccines and other treatments in many parts of the world, and some of them do not have the refrigerator. These treatments can save lives, literally, and if you have an antibody or biological structure which is temperature sensitive, that will not work. Nanoparticles do work, and they are absolutely thermally stable. So this is the big advantage here. And with that, I think I will skip the second part because it's basically all on the same topic, just different types of nanoparticles and different types of the virus. With that, these are the folks that did the work, and Anastasia, who write on this on the left side of the group, with this red dog. She was one of the key people here, and Minjong Cha, who is on the left, and Jessica Ma, who is in the middle. They were the drivers of that. With that, thank you very much. Be happy to answer your questions, and have a good time in the meeting.
I see one question coming your way.
I may have misseen something at the very beginning, but I had the impression that water had an impact on the chirality and the formation. Is that correct?
Water is achiral. So it has an effect on structure of the protein, but it doesn't have an effect on actual chirality of particles that we are interested in. But depending on how, say, pH of water, is it high or low, and what is the ionic content of water, that affect a lot the interactions of these particles and the protein.
So at the nano level, water seems to have properties that are incredibly divergent from how we think of it typically. Am I correct?
You're absolutely true.
And so how are you
correct.
imagining that plays into the, I may be misunderstanding or simplifying things, but I think of it as my right hand fitting my left hand, and that's where this confirmation of the folding and all makes sense, because they have to chirally match each other.
True.
And that's my imagination now runs toward how the water has a dynamic impact on that. And I'm also wondering about the time frame of the dynamics as to what you're seeing in terms of how quickly these things change, because they seem to have much more speed than what we might imagine, and that becomes critical, I would think, to how they behave in a full organism.
You're absolutely right that water is very essential. The reconfiguration of water molecule is faster than the reconfiguration of the proteins due to the mass. So water is just 18 at the atomic units. The proteins are in kilodaltons. So water adapts itself to the protein conformation. So it's, if you allow me, it's something that we have to take into account, but it's actually faster than the protein particle or protein interactions.
That's one more question, and that's thermodynamics.
Yes, sir.
Is there ATP that's causing all of this in your model or in your understanding of it, and how is that rate limiting and feeding all of these interactions?
Yeah, good. ATP is not included here for this model, but for other model that we're working on right now, and I'm writing this paper, I have been writing this paper for a couple of months now. It's not easy to incorporate all of the aspects, including the thermodynamic aspect. So what we're looking at the interactions of nanoparticles with G-actin, which is the protein which interacts with ATP. So it has a pocket which holds it, and after that, G-actin forms a skeleton of cells. And in this case, the thermodynamic of replacement of ATP with a nanoparticle plays a humongous role. So you're absolutely right there too.
I want to actually just put in a comment, which is I really, really appreciate how you talked about being a skeptic to actually being converted, and now like being a leader in developing advanced AI methods, especially with incorporating graph theory. And so I think the reason that I really admire this honesty is that so many people these days are coming from the other direction, which is, well, let's adopt AI, let's use it. And already there are so many publications out there or pre-publications that really are, I'm sorry, just like really not very valuable. Let me. And so I just feel like that's really inspiring.
Thank you, Ing. I have to say that for a long time I resisted using the machine learning in my lab until I got frustrated to the bottom of my stomach with our inability to predict these interactions. And eventually I said, yep, let's do it. And it worked very well. And of course, now we are developing in multiple ways. I have to say, it's not just the part that we're working in AI now. We're also working on the graph theory for the design of the materials for instance, implants. Say, structure of cartilage is very difficult. And understanding how we can design similar geometrically complex structures by using machine learning and AI faster than from just images. Of course, you have seen a number of examples. You take image, you collect hundreds of them, and you can distinguish cats and dogs. Great. But now in science it doesn't work, because each image costs thousands of dollars. You cannot do that if you have to solve a problem that requires millions of images. You have to be very frugal, and that is a part of machine learning that I'm trying to address now. So how we do the mathematical pre-processing of the images, extract the chemistry and physics from them, and then apply AI faster and with a limited amount of the images that we can obtain.
Thank you.
Thank you.
So with this, we wrap up